Welcome to the fourth lecture of this series. In this lecture, we are going to discuss about the wave packet and group velocity. In the second lecture of this series, we have discussed about the particle velocity and phase velocity of a monochromatic traveling wave. The equation of a monochromatic traveling wave is given by y is equal to a cos kx minus omega t. Here k is the propagation constant and omega is the angular frequency. Here the phase velocity was given by dx by dt, that is equal to omega by k. But in our day-to-day life, what we are observing or what type of waves we are observing, if we take an example of light wave, the light wave is not so simple, and this wave of light cannot be expressed in this equation, because this equation is only valid for a monochromatic wave. But the light wave we are observing in our day-to-day life is not a monochromatic wave, rather it is a polychromatic wave. It is a mixture of so many monochromatic sinusoidal waves. When we say about a wave, a picture like this comes to our mind. When you say about a wave, one always think this type of picture in his mind. But in case of our day-to-day life, the wave which we are observing are not monochromatic waves, they are polychromatic waves, and we can say that they are the mixture of so many monochromatic waves. So the question here arises that how these real life waves appears to us, or how these monochromatic waves, if we want to draw the shape of these monochromatic waves, how can we draw the waves? So this wave equation which is written here gives the wave which are extended from minus infinite to plus infinite, or we can say that their extension or spread is in the whole of the space. But practically, which we are observing, the waves are not spread from minus infinite to plus infinite. They are confined in a very small region, which means in a very small region there is some value of y, this y, there is some value of y, and outside that region the value of y is negligible. We can see in this picture that let this is x1 and this is x2. In this region the wave exists, and outside this region the wave does not exist. This type of figure or this type of wave we can call as a wave packet. And how a wave packet is formed? A wave packet is formed by mixing of number of monochromatic waves at a particular point. So if at a particular point a number of sinusoidal monochromatic waves mix together, they form a I-shaped structure. We call it as a wave packet. We can see here that the value of y is taken in this axis and x is taken in this axis. The value of y changes. The value of y changes as x changes. But here it is to be noticed that the value of y is not constant as x changes. The value of y is continuously varying. The value of y in this mid region is maximum and is negligible near x1 and x2. Okay, So as time passes, the constituent sinusoidal waves which construct this wave packet also move some distances. Every wave or every monochromatic wave move different distances with different velocities. And as we can see here, the velocity of a monochromatic wave is given by omega by k. So at a time del t, every monochromatic wave which constitute this wave packet will be moved through a distance omega by k into del t. And as omega is different for different monochromatic waves and k is also different for different monochromatic constituent waves, the distances shifted by each of the monochromatic wave is also different. At a later time del t, the shifted monochromatic wave will also construct a wave packet, but this wave packet may not be similar with the previous wave packet which we had got at the time t is equal to 0. It may be some difference. Some difference means it may have a large spread, or it may have a wide thickness, or it may have a more thickness than the previous one, and so on. So the wave packet which we are going to get in the time del t will be something different from the wave packet which we have got at the time t is equal to 0. As at the time del t, each monochromatic wave has traveled this much distance. At time del t, they will also form a new wave packet, and we can say that the wave packet which we observe at time t is equal to 0 is completely shifted to a new wave packet at time t is equal to del t. And the question here is how much distance the wave packet is shifted in the time del t. The distance shifted by the wave packet is the distance between two points which are corresponding to most bulk part of these wave packets. Let this is the wave packet, let this is the axis, let this is the wave packet which we have observed at time t is equal to 0. So this is the wave packet we have observed at time t is equal to 0. And at time t is equal to del t, we observe a different wave packet like this. Here we can say that the spread of this wave packet has been increased. This is the wave packet which we have observed in time del t, and as we can see that the spread of the wave packet has been increased. So how much distance this wave packet is shifted in time del t? The distance shifted by the wave packet in time del t is given by this distance, that is x1 and x2. x1 point is corresponding to the most thickened part of this wave packet at time t is equal to 0, and x2 corresponds to the most thickened part of this wave packet at time t is equal to del t. This distance del x can be considered as the distance traveled by this wave packet in the time del t. So we will here take two monochromatic waves for our to simplify our calculation. Here we will take two monochromatic waves and see how these monochromatic waves superimpose with each other to make a wave packet and we will derive the velocity of the wave packet. Here we will consider the two monochromatic waves of slightly different propagation constant and slightly different angular frequency. So one monochromatic wave is given by y is equal to a cos kx minus omega t. This is equation 1. And second monochromatic wave is given by y2 is equal to a cos k plus del k plus del k into x minus omega plus del omega into t. These are the two monochromatic waves of slightly different k and slightly different omega. Let it put equation 2. Okay. Now, if these two monochromatic waves will superimpose at one point, then let's see what will happen. According to principle of superposition, if two monochromatic waves superimpose at one point, the net displacement of the particle will be the vector sum of the two individual displacement when either wave is absent. So, net displacement y is given by y1 plus y2, that is equal to a cos kx minus omega t plus a cos k plus del k whole into x minus omega plus del omega whole into t. So we can say here, so we can apply the formula cos a plus cos b, we will get 2a cos k plus del k by 2 whole into x minus omega plus del omega by 2 whole into t into cos del k by 2 x minus del omega by 2 into t. Okay, this is the equation. That is equal to 2a cos k0 plus del k by 2, sorry, here k0, here k0 x minus omega 0 t whole into cos del k by 2x minus del k by 2x minus del omega by 2 into t. Here k0 is where k0 is k plus del k by 2 and omega 0 is omega plus del omega by 2. Here k0 is called mean value of k. This is the mean value of k, and omega 0 is the mean value of omega. So why k0 is called the mean value of k? Because for the wave 1, propagation constant was k. For the wave 2, the propagation constant was k plus del k. If we calculate the mean of k, then we will add these two and divide by 2. This will be equal to k plus del k by 2. Similarly, if we calculate the mean value of omega, then it will be omega plus del omega by 2. So omega 0 is called the mean value of omega and k0 is called the mean value of k. So the equation becomes y is equal to 2a cos del k by 2x minus del omega by 2 t whole into cos k0x minus omega 0 t. So to calculate the expression for the group velocity, we will see what time is required to travel a wave packet through a particular distance. Then with that particular distance, we will divide the time taken to get the group velocity. So for that, we will follow a process in which we will draw or we will first decide the shape of the waveform at time t is equal to 0 and shape of the waveform at time t is equal to del t, and then we will proceed to calculate the group velocity. So at time t is equal to 0, shape of the waveform will be at time t is equal to 0, shape of the waveform will be y is equal to 2a cos del k by 2 into x into cos k0 x. This will be the shape of the waveform at time t is equal to 0. Here we have just put 0 at the place of t. So here we get two terms. One is 2a cos del k by 2 into x, another is cos k0 x. If we draw a graph between x versus y for this term, we will get this figure. If we write a dash into cos k0 x, where a dash is equal to 2a cos del k by 2. If we draw x versus y for this term, we will get this equation. So in this equation, x is taken in this direction and a dash is taken in this direction. And if we draw x versus cos k0x, we will get this equation. This equation is drawn for cos k0x. We can see that in the term a dash, del k by 2 is very small, because del k, so we have to write here del k is very small than k and del omega is very small than omega. As del k is very small than k, the variation of a dash with respect to x is very slow. As we can see here, the variation of a dash with respect to x is very slow. Here k0 is very much large in comparison to del k. The variation of cos k0x is very rapid with respect to x. You can see here the variation of cos kx is very rapid or more rapid than this curve. Here as x increases, the cos x changes, and this change is very rapid or more rapid than this curve. So what about the curve? So what about the curve given by y is equal to a dash cos kx? Here we have drawn the curve for a dash. Here we have drawn the curve for cos kx. But now we are going to draw the curve a dash cos kx. Means we have to draw the multiplication of this term with respect to x. So what is the method to do that? The only method is we will multiply point by point and draw x versus y. Here the maximum value of cos kx is 1. The maximum value of cos kx is 1. So when cos kx attains its maximum value, the value of y will be equal to a dash. And a little further, this term will attain a minimum value, that is minus 1. At that time, the value of y will be minus a dash. If keeping in mind these two terms, a dash and cos kx, we will draw the figure will be like this. Here we can see that the amplitude of this wave or amplitude of this curve at time t is equal to 0 is not constant. Here at some region the amplitude is 0. Here at some region the amplitude is maximum. We can get this curve using any software in your mobile phone or computer. If we put these two functions, we will get this type of curve. Okay, so this type of curve or this type of picture what we are looking here or what we are finding here is called a wave packet. So the position of the wave packet or the shape of the wave packet at time t is equal to 0 will be like this. And now we have to determine or we have to decide how the wave packet look like or how much distance the wave packet will travel after a time del t. Here we can see that this waveform is changing less rapidly than this waveform is. So we can say that this waveform given by a dash is guiding the second waveform. How we can say this, that this waveform is guiding this waveform? We must not say that this waveform is guiding this waveform, but we are saying that the waveform 1, that is a dash, is guiding the second waveform. How we can say it? Look at this region. In the absence of this waveform, the second waveform will have this much amplitude at this point. Due to presence of the first waveform, the amplitude of this mixed waveform is 0 here, and this amplitude is equal to the amplitude here. Okay, so we can say that the second waveform is guided by the first waveform. Similarly, at this point, if this first waveform was absent, the amplitude at this point would be this much. But due to presence of this first waveform, the amplitude is this much, which is less than the maximum amplitude. So we can say that the second waveform, that is given by cos kx, is guided by the first waveform given by a dash. So the velocity of the waveform given by a dash can be considered as the velocity of the wave packet. Here we can see that the expression for a dash is given by a dash is equal to 2a cos del k by 2 whole into x. This is the expression for a dash. And just before we discussed that the curve a dash is guiding the second curve, so we can say that the traveling velocity or velocity at which a dash travel is the velocity of these wave packets. So in this case, so we have to write here the general equation of a dash. This is the equation of a dash at time t is equal to 0. General equation of a dash is given by a dash is equal to 2a cos del k by 2 whole into x minus del omega by 2 whole into t. This is the general equation of a dash, which we had written earlier was the equation of a dash at time t is equal to 0. So from this equation we can see that here del omega by 2 is the angular frequency and del k by 2 is the propagation constant. We have learned from the equation of a monochromatic wave is that if a monochromatic wave is given by a cos kx minus omega t, the velocity of propagation of this monochromatic wave is given by v is equal to omega by k. Similarly, the velocity of propagation of a dash will be equal to the ratio of angular frequency and propagation constant. That will be equal to we can write velocity of propagation of a dash will be equal to del omega by 2 divided by del k by 2, that is equal to del omega by del k. So this is the velocity with which the curve or the wave a dash travel. And as we have discussed earlier that the second wave is guided by the first wave. So we can say that the velocity of the group or the velocity of the wave packet is equal to del omega by del k. Okay. So here we have discussed the wave packet considering or keeping in mind the two monochromatic waves. But in our daily life, what we are observing in case of light or in case of sound, they are not made up of only two monochromatic waves. They are made up of numerous monochromatic waves. Then in that case, what is the expression for the group velocity? Let us discuss a little bit about that. So as I said, in our daily life, the monochromatic wave or in our daily life, the wave packet is made up of a numerous monochromatic waves, and their k and omega varies continuously. For a definite omega, there is a definite k, and vice versa. So in this case, and there is a definite omega for a definite k, and secondly, the omega and k are continuously vary. So in this case, we can say that omega is a function of k. How can we say that omega is a function of k? Because in our daily life, what type of wave or what type of wave packet we are observing, this wave packet is made up of a numerous monochromatic wave having different k and different omega. and these values of omega and k are continuous, and also for each omega there is a value of k. So we can say that omega is a function of k. So if we apply the velocity of propagation of a Gaussian wave packet in this case, we can replace del omega by del k by d omega by dk at k is equal to k0. K is equal to k0. So we can say that the velocity of a real wave packet means the wave packet which is considered to be made up of numerous monochromatic waves instead of only two. In this case, the velocity of wave packet, that is del omega by del k, is replaced by d omega by dk at k is equal to k0. And k0 is the mean of the propagation constant, and which corresponds as omega 0 is the mean of the mean of what we can say the angular frequency. So this is all about the group velocity and wave packet. Okay, thank you.